CrossKeys, text entry for virtual reality using a single controller via wrist rotation. Texting has long been an indispensable part of people's lives. Countless scenarios, like online chatting and searching, cry for an efficient input method. On traditional electronic devices, text entry has been widely applied, such as the most omnipresent QWERTY keyboard for personal computers, and the T9 keyboard for mobile smartphones. Notwithstanding, in virtual reality, even with the fast development itself, an efficient and handy text entry method for such an environment is still wanted. Although there are already several text entry methods being introduced, such as pizza text, HiPad, and ring text, they are all constrained by two-dimensional mapping. Few methods are employing the three-dimensional space, with which text entry could perform much better. In this paper, we introduce CrossKeys, a novel, efficient, handy text entry method for virtual reality. Compared with precedent methods, our CrossKeys employ the 3D space of the virtual reality environment, expanding traditional manipulating space dimension from 2 to 3, thanks to which the performance of our CrossKeys is a highly efficient kind of text entry method for virtual reality. In the user interface system of our CrossKeys, there is an inputting field and a list of 3 auto-completion candidates. The main part is an arch cross with 7 character blocks on it. Each character block contains 4 characters, arranged up, down, left, and right. Overall, there are 28 characters available, consisting of 26 English words and 2 special symbols, comma and period. They are distributed in alphabetical order on these 7 character blocks. The controller is also visualized in the system with a pointed stick. There are 2 kinds of areas, 1 activated area, and 4 deactivated areas. When selecting and entering a normal character, excluding blank space, after moving the tip to the activated area, turn the wrist to point to the character block where the target character is located, making it highlighted. At this time, according to the position of the target character in the block, gently touch the corresponding position on the touchpad to select and enter it. When selecting and entering an autocomplete candidate, once the target word occurs in the candidate list, move the tip out of the activated area into any of the 4 deactivated areas. At this time, according to the position of the target word in the candidate list, click the touchpad on the corresponding position, left, middle, or right, to select the target word and enter. A blank space can be entered at any given time by simply clicking the grip button to enter a blank space. Notice that the occurrence of blank space will interrupt and reset the current autocomplete prediction. When deleting a character, pull and click the trigger to delete a character at the tail of the current entering sequence. We design a pilot user study to decide on the best layout of CrossKeys. We first give 3 layouts with different letter distributions, alphabetical order, QWERTY-like, frequency order. The result shows that the alphabetical order layout is significantly faster than other layouts in WPM with similar error rates. We then highlighted the letter blocks, which the user pointed to see whether more user interaction feedback could exert any influence. The conclusion is that the highlighted version of CrossKeys is significantly faster than the previous version, and no significant effect is shown on error rates. We design a user study to evaluate our method. Task 1 requires the user to type 45 minutes per day for 3 consecutive days. After this, the user needs to enter 15 phrases with their possible fastest speed and highest accuracy. On the 3rd day, the average WPM reached 17.73, and one participant has reached 24.73 after entering 1 set of phrases. Data of 3 days have similar error rates. Task 2 requires the user to incessantly enter phrases for 3 rounds, 2 minutes, 6 minutes, and 10 minutes. Before the first round, one can practice for 45 minutes. No significant impact was made on WPM and workload, and the increase in error rate is slight, indicating that CrossKeys has relatively good fatigue resistance. Task 3 requires the user to enter phrases under stationary and in motion circumstances. No significant impact was made on WPM or error rates, and the average WPM reached 17.37 under motion circumstances, which indicates that CrossKeys maintains adequate stability during moderate motion. In conclusion, this video presents our CrossKeys, a text entry method for virtual reality using a single controller via wrist rotation, which is designed to fully exploit the 3-dimensional space provided by the virtual reality environment to improve text entry experience and performance. As our anticipation, the experiment date of our CrossKeys turn out well with the best WPM of 24.73 and an average WPM of 17.73. We could reasonably affirm that our CrossKeys is efficient, easy to learn, and can be widely applied to controller-based virtual reality devices.